Okay, welcome back. So I'm Kfir, I'm from Basis Technology. And my topic for today is how we keep up with evolving languages. So NLP, or natural language processing, is all about processing text, completely unstructured, either to find some useful structured information or to generate an alternative text, like in machine translation, document summarization. The output format is basically defined by what we call an NLP task. And the input can be anything between fully grammatical news article and an informal instant message. So the focus of this session will be on how we build models that can handle different domains and genres. So there are many NLP tasks out there people try to solve. This is a partial list that I took from NLPprogress.com. And each task is usually provided with some the current state-of-the-art results. And then different research teams from all over the world are trying to improve on that, typically using all those transfer learning models, autoregressive models that people are using today, and they're coming very fast these days. So we feel a little bit like Jon Snow here. But anyway, in the industry, there's a lot of interest in a subgroup of all these tasks, specifically like relationship extraction, sentiment analysis, summarization, classification, and more. And of course, named entity recognition, which is probably one of the most popular tasks in the industry. So I will focus on this task, so let me give you some background and some definitions first. Named entity recognition is about finding names of people, organizations, locations, and some other types in plain running text written in different languages. Let me give you an example. Elon Musk says building the first sustainable city on Mars will take 1,000 starships in 20 years. So Elon Musk is highlighted in blue here. It means that it's a person entity, let's say, and then Mars is a location, right? So this is how we want to shape the output to detect where are those entities, and also we want to know their types. Now, maybe some of you think that it's a simple task. Let's just compile a list of location names, let's say from Wikipedia or something like that, and then run a simple lookup procedure to find instances of that list in the text, and we're done. But of course, then you won't know whether Mars is mentioned as the location or the candy bar, right? So you need a context to help you resolve these kind of ambiguities. There are more such examples. Let me give you another one. So here, let's say Israel has since become most associated with, let's pick an ending to this sentence, let's say citrus fruits, right? So it means that Israel here, it's the state of Israel, it's a location, if you want, a geopolitical entity. And the variability of the context that can help us resolve this ambiguity, knowing that Israel is a location, is huge, right? There are many different endings that we could pick for this sentence, right? And then that it will help us determine that it's actually the state of Israel, right? Something like that. But what if we pick a different ending to this sentence, something like jazz pianist Bill Evans? So now Israel is actually no longer the state of Israel. It's a name of a jazz standard played by this guy, Bill Evans. So it has a different entity type. The time is also an important context component, right, for resolving ambiguities. Like before 2017, if you said Bert and Elmo, are probably referring to these guys, right, from Sesame Street. But after, it's different, right, especially in this community, so referring to all these autoregressive transfer learning models. So I hope I'll say that named entity recognition is probably one of the most important tasks in NLP. Especially if you're talking about information retrieval. It all begins with entities, and then you'll try to find or kind of to build a narrative that connects all the entities together, something like relationship extraction, event extraction, sentiment analysis, and so on. So in that sense, I would say that entities are kind of the backbone of a document, or a collection of documents. I hope I convinced you that it's an important and non-trivial task. At Basis, we have a bunch of capabilities around this task. Specifically, we employ a couple of data-driven machine learning algorithms to detect entities and determine their types. We have one that is based on a recurrent neural network, and another one which is more like a traditional machine learning algorithm based on structured average perceptron. Now, what you see here is some evaluation results for different languages. This is F-score measured over our own annotated corpora. And you can see that the neural model is slightly better, sometimes even significantly better than the traditional model across the board, all the different languages. But it's also slow, or slower. But it's a different, maybe another topic for a different talk. Specifically here, I want to focus on this. So to train all those models, we use news articles annotated for people, locations, organization manually, but there are news articles usually in all those languages. And then we train those models. So applying those models on an unseen document, news articles, makes sense, but it's probably not going to be very effective when you try to apply it on an instant message or something like that. So in that sense, I would say that a model, among other things, has three main characteristics. One is the language, and then we have the domain and the genre. The language is something that I'm not going to talk about today, but it's an important topic that we can talk about. We're doing a lot of things in this area too. But specifically for domain and genre, so the domain defines the content of the document, so news, financial, medical, travel, and so on. And I would say that two documents that are coming from two different domains will probably differ in the content words that they're using, like nouns, verbs, adjectives. They will also probably have different entity type distributions. For example, probably financial documents will have more company names. Travel documents will have more location names and something like that. The genre is more affiliated with the style of writing, right? It's a little bit different. So you have fully grammatical news articles or application letters. And then we have microblogs, right? Like Twitter, Facebook. Web forms, chats, and speech transcriptions even, right, and SMS, instant messages. Those can be very idiosyncratic, right? So someone from outside sometimes won't understand anything about what I'm writing on my phone. So we would like to explore examining the differences between the different genres. So here specifically, we'll look at text or chunks of text of 4 different genres. We have news articles, instant messages, chat rooms, and speech transcriptions. And we took a sample of about 50,000 words of each one of them, which we used to calculate a few things that I will show you next. The news articles were selected from a few popular media outlets. And then the instant messages were donated by a relatively large number of people. And they were pretty short, as you can see on the last row of this table, the average item length. The chat rooms were also donated and were also sampled uniformly for different demographic groups. And the speech transcriptions are basically meeting minutes of a few groups at Carnegie Mellon University. They were manually transcribed, so it's not automatically transcribed. So they follow a strict transcription guidelines, including a very consistent way of doing word casing, similar to what we have in news articles, basically. So the first thing that we noticed is that if you look at the data, I mean, you identify that people that use instant messages, chat rooms, they like to compress their message, right? We like to write short things. So, for example, this expression, I do not know or I don't know, becomes something like that in chat rooms, or even something like that. But then in speech, it's slightly different. We also like to compress things, make them shorter, but in a slightly different way. So we want to say things that are easier to pronounce, right, and not easier to write. So IDK is a little bit difficult to pronounce, so we'll use something like this, right? I don't know. So we took a sample of the 50,000 words, and then out of these, we took the 3,000 most frequent words of each genre, and we calculated the number of shared words between every pair of corpora here. So the numbers that you see on the links here is the percentage of similar, identical, frequent words between every two genres here, right? And the thickness of the lines will help you visualize that. So you can see that instant messages, for example, on the top there, they're more similar to chat rooms and speech transcriptions than to news articles. Not a big surprise, I guess. Generally speaking, if you look at this, news articles are different than everything else in this context, right? Now, if you think about this, frequent words are usually affiliated with functional words. Those are not content words, right? So less related to content. So they're more related to the style of writing. So in that sense, news articles are different than all the others. Another perspective for that is maybe this one. Here we took the K most frequent words, or we summed all their mentions in each one of those corpora, and then we divided it by the total number of words, tokens in each genre. And we're using a running value for K. So specifically, if you look, for example, at the green curve representing news articles, where K equals 500, for example, right? So you can see that the 500 most frequent words in news articles cover something like 70% of the entire corpus. It sounds a lot, but it leaves about 30% room for other words, right? Infrequent words, which are more related to content. That as opposed to all the other corpora, informal genres, let's call them, that leave much less room. And also you can see that this green curve grows slower than everything else, suggesting altogether that news articles have more variability in content. Here we took, we actually annotated 40,000 words out of each corpora. We annotated them for people, location, and organizations manually, following an annotation, our own annotation guidelines in English. And then we calculated the entity per word rate, right? So it's like total number of entities divided by the total number of words. And then what you see here is that news articles are more dense. They have more entities in them. And this is, of course, an important observation because if you want to annotate documents and build a new model, so for chats and speech transcriptions, you'll need to annotate more. So I have more such observations to share, but I had to cut a few slides so that we can talk about some other things. So I'm going back to this slide. This is when we talked about, that we're using news articles or annotated news articles to train our base models, right? So based on these differences that we've just observed, hoping that this model will work on instant messages just doesn't make sense. So we would like to explore different ways of doing adaptation, right? So to take that model, and that word was mentioned before during this day. So we want to take that model, the base model that was trained with news articles, and then do something, adapt it, add more data, and then create a new model that works on exactly what we need, like instant messages, for example. So before this slide, I would say that at Basis, we have two approaches that we follow. One is completely unsupervised, which I'll mention here. Another one is supervised. But there are many other research directions of how to do domain adaptation. So for the unsupervised approach, I want to first discuss one difference between traditional machine learning and deep learning. specifically in the way that we treat the input. Right? So with traditional machine learning, you take the input text, and first you extract some features out of it. Right? Like we break the text into words, take part of speech tags, lemmas, pre-process the text, and all these linguistic features, you can use them to train a model. We also use semantic features with traditional machine learning, like word clusters, for example. If you like, it's like a more primitive version of word embeddings. And we create them using a large corpus or a large collection of documents, unlabeled documents, and then we basically cluster words based on the surrounding context. And then with deep learning, we typically encode the text with embeddings first, right? So we just use vectors to represent words, characters, subwords, depends what you're doing, right? But those vectors can also be pre-trained ahead of time using a large collection of unlabeled documents. So word clusters and embeddings capture more semantics or meaning, right, rather than structure and morphology. So in the unsupervised approach, what we do is we're trying to take a large collection of documents, unlabeled documents in the target domain. So let's say financial here, financial documents. And then we fine-tune those embeddings and word clusters. And once they're fine-tuned for this particular domain, we can take them and then use them to train a new model, adapted model, let's say, using the annotated news articles that we already have. We don't need to annotate more documents. Now, for embeddings, it's still an ongoing research in our lab, so we're trying to do different things. Among them is to take transfer learning models like BERT and trying to fine-tune BERT on the language model task specifically to adapt those embeddings to work better on a target domain. Unfortunately, I still don't have any results to share there. But with word clusters, using our own technique for doing word clusters, a pretty simple one, we were able to show some significant improvement specifically in this domain in English. So you can see the before fine-tuning and after fine-tuning, some significant improvement. Now, it probably won't work as good for genre adaptation because we said that embeddings as well as word clusters capture more semantics, meaning, right, and less structure, morphology, and functionality. So this supervised approach that we are following is pretty simple, right? You just need to annotate more documents. But then the problem with annotating more documents and then maybe to combine them with another set of documents that we already have, the news articles, is a bit problematic because maybe the new documents will have a different word distribution, entity type distribution, right? Different vocabulary. So what we typically do is we just create two different models, right? So we train the base model like before, and then we train a custom model using the annotated data that we just created for the new genre. Now, annotating data is a very difficult task, I have to say, right? You need to follow guidelines. If you have multiple annotators, it takes time to train them and so on. So I'm just want to make sure that we understand that. Once we have those two models, we use both of them in parallel. So we apply both of them on an input text unseen document. And then we have another component, which I didn't put it here, and I'm not going to talk about. It's a component that takes all those, the outputs from the different models and combine them into a final output by resolving some conflicts that are coming from the two other models. So here we ran an experiment, specifically an experiment for genres. So what you see here, we took the 40,000 words that we annotated in each genre, and we used some for training, some for evaluation. So every big column here, like we have 4 of them, so every big column here represents a specific evaluation package for a specific genre. Now, and then for every genre, we use different combinations. So the blue bar represents news article, the base model, and then we have all the other combinations. So base model and chats, base model and speech, and so on. So for example, if you look at the second big column from the left, the chats, You can see that the red bar is where we got the best results, and obviously this is where we took chat room documents or chat room text, annotated them, and created a custom model, combined it with the news model, and we got better results significantly at this point. And it works the same for all the other genres. The disappointing part, of course, is, as you can see, I mean, the results are pretty low, right? So this is exactly what we said at the beginning. So taking a news model, right, and try to apply it on other genres, not domains, is very problematic. So you get very low results. Now, we're hoping that we can improve those results, and this is just the beginning of this work, and improving with more data, for example, yes, because we only annotated 40,000 documents, makes sense. But we can also say that it's probably a more difficult task than annotating news documents. As I said before, the language can be very idiosyncratic. It's very difficult to understand. So we do plan to measure human-level accuracy on this task, and we believe that it will be much lower than human accuracy on news articles. On domain adaptation, this technique works pretty well, as you can see here. So we just took news documents, financial documents for evaluation, and then we used the blue bars where we used the base model, and then the base model with a custom model, which we trained using financial documents. So we got significant results. So that brings me, I think, to my last slide. I'll just say that I hope that I convinced you that just improving state-of-the-art results for the traditional named entity recognition task is probably not the only thing that matters. And it's very important to be able to move from one domain to another, from one genre to another, in the real world specifically. So it's important that we continue to explore these ways. I think we're only starting, and for NER and for other NLP tasks. And that's what we're planning to do. So thank you very much for listening and for coming here.